Hi, today I want to look at the ALU and some of the foundational components we're going to need to start pulling that together. We'll lay out the design. Here we go.
Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey.
Let's start by laying out some of the design goals. I really want to make sure that every instruction that goes through the ALU is a single instruction cycle. If I have to add an additional stage to a pipeline and turn the CPU into something that has two instruction register stages, then it's no longer a RISC computer, reduced instruction set computing RISC. It's no longer a RISC CPU, if you will. And I really do want to try to keep that as everything is a single instruction cycle. I do want to have a robust suite of ALU operations, a number of shifts and rotates and adds and subtracts, and a number of logical instructions as well. That robust suite of ALU operations instructions that I can add into the CPU also is limited by the number of instructions I can have in my instruction set. That introduces a new complexity that I need to sort out. We'll talk about that in a few minutes here. Now, as far as multiply and divide, those are not going to be able to be done in single instructions, not without a massive lookup table and have everything pre-calculated, and all it does is look up the value. I'm going to instead rely on software support for multiply and divide. This is no different than what James Sharman did in his ALU. I do want to flatten the ALU, meaning I want to have a very short path of gates from the inputs to the outputs. That means I'm going to end up stretching out the operations wide across the ALU with inputs going to several different things at the same time. But I will select which output goes back onto the main bus based on which instruction I'm actually executing. Ideally, I don't want any one section to feed into another, but I don't know that I can actually accomplish that because part of the subtract instruction is going to be to invert the input of the second argument. And I don't want to have a second stage that has to do that inversion. So I'm going to have to figure out how I want to path all of that properly. What I did is I went out and took a look at what instructions were available on several different CPUs. This is not a comprehensive list. I know I have left some instructions off of the list, and I know that I've likely missed a few as well. Some were deliberate, some were by accident. But what I wanted to do is I wanted to get a sense of what instructions were available on different CPUs so that I could make a reasonable estimation of what I wanted to do on my 16-bit computer from scratch. And so you can see the different things that are available by different CPUs, but the right-hand column is what I intend to implement. So real quick, I've got add with carry, subtract with borrow, increment, decrement, and negation. Now negation can be a subtraction of a register from 0. Pretty reasonably simple to implement. Increment is incrementing by 1 or adding 1 to a register and putting it back out onto the bus. Decrement is subtracting 1 from the register and putting it back out onto the bus. Those will be relatively easy to implement. Of course, add, subtract. Subtract being a bitwise inversion of every bit in the second argument, add 1 to that, and then you can do an addition to the first argument at that point. Bin Eater's got a good video on that. So that said, these become the targets of how I want to take care of the arithmetic instructions. Looking at the bitwise logic instructions, I did the same thing. I went out and looked at what instructions were available across several different processors, and I've decided I'm going to implement and, or, exclusive or, and not. Not is an interesting one because you can actually exclusively or a value with a 1 for each bit is turned on, and effectively perform a not on that. But that, of course, takes an extra byte in the instruction stream, or word in the instruction stream in my case. So I've opted to include that here just to make that a little bit simpler and reduce the number of bytes or words I have in my programs. Finally, here we've got the shift instructions, and this was a little bit interesting for me. The 4 instructions in yellow I had not considered implementing. And as I was doing research for this video, I did a little bit more digging into these instructions, or their equivalents across other CPUs and decided to include them. And then ultimately the logical shift left, or LSL, and arithmetic shift left, ASL, are really the same instruction. There's no functional difference between them. There's no difference in the result of those instructions. They both shift to the left and zero fill the least significant bit of what's being shifted. The big difference is in the readability of the code, so I'm likely going to implement one of those and then have a second instruction of a different name that performs exactly the same function, just to aid in readability as you're writing code. Finally, I'm going to need to have the ability to directly manipulate the carry bit in the flags. Might or might not need to be able to directly manipulate the overflow flag. I'm not quite sure yet, so I've got those listed in question marks. But certainly I am going to need to be able to directly set and directly clear the carry flag. So I have those instructions set aside as well for this. So my plan is to start with a typical 4 flags that an ALU would have. So there would be some carry. Many instructions will actually impact that carry flag. Overflow for signed operations. A negative flag, which some call a signed flag, but a negative flag, which is going to be directly taken from the most significant bit. And then a zero flag, meaning all the bits are zero. And I'm curious if I can get tricky by using the LEDs as diodes and then use an inverter of that and tie them all together. I'm not sure I'm going to be able to do that, but it'll be fun, a little experiment to take on. Now, what's interesting about the overflow flag is I did find an article online that indicates that the carry out from the 14th bit of an operation exclusively ORed with the carry out of the 15th bit of the operation will indicate whether or not an overflow has happened. So I'm sure you're going to ask, Adam, if you're going to use a full adder, how do you get access to bit 14 for the carry out? I've got some plans for that, so stay tuned there. Now, because of the way I want to condition my instructions, similar to the way the ARM v7 has, I want to introduce the concept of an L flag. This L flag will be, or mean less than, and will be calculated as in the N flag or negative flag is not equal to the overflow flag, the V flag. Or, in other words, the N flag exclusively ORed with the V flag, and I've got a table there off to the right so that you can see how that would work out. This is just going to be pre-calculated and latched with all of the other flags as needed so that it becomes easier to determine if I have met a condition or not in runtime. Each flag, each of those 5 flags now, so the 4 normal ones and the one that I'm introducing, are also going to have a pre-calculated inverted form. So if the carry flag is 1, I'm also going to store an inverted carry flag is 0. Well, why would I want to do that? Because I don't want to add extra time, extra nanoseconds in order to calculate the inverse of the carry flag, or each of those flags to be specific. There's also going to be 2 additional flags, one to indicate if my program counter and return address register are in a swapped state, and then another one to indicate whether I'm in a program context or an interrupt context. And those will be used later in the processor build. But the X flag will be hardwired such that I've got a program for 0 and 1 for interrupt. And you can guess that I'll end up with 2 sets of flags if I'm going to hardwire that particular bit. So I mentioned earlier that I ran into a problem fitting everything I wanted to be able to do into 16 bits worth of instructions. What I had intended was for these 8 bits to indicate what instruction was going to be looked up in the control table. And I had several additional bits that were unused up at this end of the control table lookup. Well, I've since decided that 256 instructions just aren't going to cut it, because some things are going to assert onto the main bus, and those will be by register that are being handled, and some things just aren't going to be able to do that. And 256 instructions were going to leave me a little bit short. So what I did is I instead added on the extra 4 bits here, giving me a total of 4,096 instructions. Took the 4 bits of the control table lookup and moved them and added them into the instructions. So now I've got full 12 bits of instruction that are going to be looked up. I haven't made these changes on the build yet, but this is now the new direction that I'm going to go. As I mentioned, I've got an X indicating which context I'm in, be that program mode or interrupt mode. And then I've got an S flag, which is going to indicate whether or not my PC and RA are switched or not. S switched. And then I'm not certain about this C flag, but what it would be whether or not these conditions were met against all of the other flags, and then I would use this down into this C flag. I may or may not need that flag, and because I may or may not need that flag, that could be potentially used for something else. So I'm using it as a placeholder for now, but I will likely come back around to that at some point in the future and decide if it actually is required or not. So now that brings me to conditional instructions, and what I need to do is to be able to evaluate any of these different conditions, always, never, equal, not equal, carry set, carry clear, etc., all the way down. I'm not going to read them all. But I need to evaluate each of these conditions to determine if that condition has been met, and then if that condition is met, is the instruction therefore going to be executed? And so if the instruction is always going to be executed, I basically am going to have a constant 1 that's always going to be evaluated. Never is always going to evaluate to a 0. 0 is a simple test against the 0 flag, or equal, which is also calculated by using that 0 flag. Not equal is this inverted 0 flag. Now remember, I said I wanted to pre-calculate or predetermine the inverse of each of these flags so that it made it easy to handle that. And what that is going to allow me to do is I don't have to do any calculation to determine if this not equal has been met or not. I just look at this particular flag. And you can look down the list here. It's relatively simple to follow until you get to unsigned higher, where I've got a complicated or non-trivial condition where 2 things need to be evaluated. And then of course I'm going to need a 2 input AND gate in order to calculate those. Similarly, if I've got, for example, lower or the same, instead of using an AND gate, I actually need to OR these 2 together, and I need a 2 input OR gate in order to make that happen. And then here's my newly introduced L flag, which is being used directly. And then that L flag is also being used in some complicated decision making as well, farther down in the list. Now all of this is not taken directly from the ARM v7 ARM architecture reference manual, but it is my inspiration for all of this. With all of that, I decided I was going to go out to CircuitVerse and model these flags and how I wanted them to work. And I went ahead and I developed out a 74HC74 IC, and that is here, which is effectively just 2 D-type flip-flops with set and reset. So I grabbed the flip-flop, D-type flip-flop, and modeled that into a 74HC74 integrated circuit, which then allowed me to bring that into my flags model. And so what you can see here is I've got several control signals that are coming into this. I'll get to what's going on over here on the left here in a minute. But if my 0 result is 0, when I latch that, you can see my 0 and not 0 change immediately. And conveniently with the flip-flop, I have both the Q output and the inverse Q output that are delivered to me right from the IC. So I don't have to do anything special in order to calculate the inverse Q. So if I want to set that to be a 1, when I clock this, this goes high, and you'll notice that these 2 change. Similarly, I've got a carry, and then I've got set carry and clear carry. Now clear carry and set carry, they happen when it's basically an active low signal. So as long as that's set, no matter what we try to latch, it doesn't matter because this is already set and that's modeled properly for the behavior of the IC. Same thing with negative, same thing with overflow. Now, what I've done is I've gone out here and I've calculated this L flag, and I've done this in this circuit. And that's latched based on either the overflow latch or the negative latch happening. And then I had to put some timing delays in here. And one of the tenets I spoke about early on in the build was I wanted to remove anything that was timing related or dependent on how the operation of any given module worked, and have that be each module be native. In other words, I wanted to make sure that I didn't have to handle any timing concerns in module, and I would handle those in the control logic. So all of this delay here really needs to be pulled out, and I'm going to create a new control signal called less than latch, and it will be the exclusive OR of those two values. I'm not going to change this aspect of it, just the control aspect of it, so that the control is native here on the board as possible. So let me pause the video here and get that done, and I'll come back and show you what that looks like. Okay, so with that removed, I now have this new less latch, which now will be controlled from the control logic. Let's build this. This is a 74 LS74 IC. This is again that dual D-type flip-flop. So there's actually one on the bottom and one across the top, and I'll stick a pin diagram up there. And I need 5 of them for each flag, but I also need to build 2 of these. So in building 2, what I need is one for the program flags and one for the interrupt flags. And that should give me what I need in order to maintain state when I'm changing from interrupts to program mode back to interrupts. Now, power and ground are, of course, needed. So ground being in its normal spot here. I do need to be able to hook up clear so that everything is cleared by a single signal. And I'm just going to grab a bunch of these hookup wires here. Now clear is pin 1 and pin 13 on each IC. Then I need to hook these all together. Then ultimately I need to bring them over here to a clear signal that's going to be at this point tied high, but I will use that then to reset to clear and then bring it back high for normal operations. I also need to wire that clear signal into, and I'll put it up here, I guess, 74 LS08. That is an AND gate, and that needs to go into one of the inputs of the AND gate. Let's see here. Let's get power and ground in there first. That'll actually go into 2 inputs. It'll be 2 different AND gates. The other input of each of those AND gates is going to be a clear carry signal. So I'll set those there. Those will be my inputs. And then changing this, if this is going to be the IC I use for carry, the output of this upper one is going to go to the upper clear, and then the one that's coming off the lower is going to go to the lower clear, and I need a longer hookup wire for that one. So the lower is going to come down here to the lower clear on pin 1. Sets are all going to be tied. Let's see, that's pin 4 and pin 10. These are all going to be tied high. And I need some longer wires here. So pin 4 and pin 10. And so the key with the sets here, with the exception of the carry, is that it'll never actually directly be turned on or set. And now for my carry, I need to have a set carry and a clear carry for each of those. Now for my data input, this is going to be pins 2 and pin 12. So the next thing along is I want to have the 0 flag. So that's going to go to pin 2 and pin 12. I'm going to need some longer wires here. And then I need a 0 latch. That's going to be pin 3. And you'll see that I'm basically just walking this across each of the flags here, making the inputs after the carry inputs, or the carry controls, direct controls. Okay, finally, the less than is going to go through an exclusive OR. So let me get that dropped in and powered up, or power and ground hooked up. And so the output of one is going to go to the input. The output of the other is going to go to the input. And then the latch signals are going to come all the way over here. And so now I need to get the inputs into each of these. Now, input number 1 is going to be the V and going to be the N. So these are going to be Q, which is pin 5. So pin 5 here and pin 5 here. Now these are going to go to this left-hand side or right-hand side gate. And then pin 5, or I'm sorry, pin 9. Pin 9, and those are going to go to these two inputs. Now, theoretically, that's all the wiring that I need in order to implement the two flags registers. The only thing that could be added to this is a place for all the outputs to come and get those all organized as well. But I think what I need to do is I need to get this all wired up and situated so that I have all my control lines here and get them at least identified and sequenced so that I can keep track of those. And let me work on getting this cleaned up. That completes the wire up here. For most of it, I just need to get the outputs and then determine how I'm going to pass this on to the instruction register. All right, as I record this, I checked and my PCBs are inbound. I expect them in 2 days from today, which is, of course, the day I'm recording this, not the day that you're viewing this. So now I've got a decision to make. Do I wrap up this flags register build, or do I start interspersing some of the PCB builds into this? And I think I'm going to start interspersing some of the PCB builds in. I've got a lot of PCBs to build, so it'll be good to start getting that stuff moving. So I'm not sure if doing all of that pre-work in CircuitVerse helps you, but it certainly helped me identify that there were some timing issues that needed to be sorted out before I started dropping this onto the breadboard. So I think I'm going to continue to do that, at least for myself. If you'd like to see that work and keep up with that work, let me know in the comments, please. In the meantime, I need to work on how I'm going to integrate this into the instruction register, and look for that in an upcoming video. Thank you. We'll see you soon.